High deep learning accuracy often masks a profound opacity. The why remains an enigma. This black box nature hinders trust in critical evaluation. Grad-CAM, or gradient-weighted class activation mapping, cracks this opacity for convolutional neural networks. It pinpoints exactly which regions of an input image contributed most to a specific classification decision. It functions by leveraging the gradients of the target class score with respect to the feature maps of the final convolutional layer. These gradients essentially represent the importance of each neuron for that decision. They tell us how strongly each feature map location influenced the output. These raw gradients are then globally averaged, generating a weight for each feature map. This weight reflects the overall importance of that particular feature detector for the predicted class. Finally, these importance weights are combined with the forward pass feature maps themselves and passed through a rectified linear unit, or ReLU. This step selectively highlights only the positively contributing pixels, creating a compelling visual heat map directly overlaid on the original image. Consider medical diagnostics. A CNN might classify an X-ray as malignant with 99% confidence. Grad-CAM can then visualize precisely which anatomical structures or even subtle textural changes drove that verdict. This helps clinicians validate the AI's reasoning, ensuring it isn't fixating on irrelevant details like a hospital stamp or patient marker. Traditional occlusion sensitivity maps involve systematically masking parts of the image, rerunning inference, and observing the drop in confidence. This is computationally expensive and often provides a coarser, less localized explanation. Grad-CAM, by contrast, is a single-pass method after backpropagation, yielding finer spatial resolution without architectural modifications required by older CAM methods. However, Grad-CAM isn't without its caveats. It can struggle with gradient saturation on strongly activated features, potentially producing less discriminative heat maps for adversarial examples or highly confident predictions. This is a subtle limitation, often leading to noisy or overly broad activations that don't precisely localize the true decision boundary. Emerging techniques like ScoreCAM or LayerCAM aim to mitigate these gradient-based instabilities, offering more robust visualizations by weighting feature maps differently. Ultimately, visualizing model focus isn't merely about debugging. It is about fostering critical trust, revealing subtle biases hardwired into training data, and accelerating scientific discovery by highlighting previously unseen patterns that drive intelligent systems.